So today's topic is EnviroDIY.org, a resource for do-it-yourself, real-time, low-cost environmental monitoring solutions. Our speakers today are Dave Arscott and Shannon Hicks. Dave is the Executive Director and Research Scientist at Stroud Water Research Center. He's a stream and river ecologist and has published research on riverine biodiversity, biogeochemistry, floodplain ecology, ecohydrology, and land-water interactions. He has field experiences that range across the U.S. and globally, from the European Alps to the Southern Alps, from the Arctic to the Antarctic, and in Central America. He received his PhD from the Swiss Federal Institute for Environmental Science and Technology, his MS from the University of New Hampshire, and his BS from Central Michigan University. Dave co-leads Wiki Watershed and EnviroDIY.org initiatives with other Stroud Center team members. Shannon Hicks has been developing, building, and deploying environmental sensing devices since she received her BS in electrical engineering in 2000. Since Shannon joined the Stroud Water Research Center in 2010, her focus has been on developing environmental monitoring solutions using the open source Arduino, I believe that's how that's pronounced, but you guys can correct me on that, electronics platform. She is a co-founder and primary contributor of EnviroDIY.org. So Dave, I believe you'll be going first, so I'll open up the presentation pod here and you can take it away.
Yeah, thank you, Brian. Hopefully the volume is still appropriate for everyone.
Volume is good.
Good. Share my screen and see what we get. Hopefully everyone sees our opening slide. All right. Well, thank you, Brian, and thank you, Penn State Extension, for having these webinars. It's a great forum to share work from around the state, and hopefully you all attending today find something interesting here with our EnviroDIY initiative. I'm going to provide most of the content today with Shannon as my technical backup, and I anticipate some of the question and answers. Shannon will jump in there, but why don't you just say hello quickly, Shannon?
Hi, everybody.
All right, so today's webinar, EnviroDIY, Do-It-Yourself, Real-Time, Low-Cost Environmental Monitoring Solutions. This is an initiative that Stroud Water Research Center launched formally with a website titled EnviroDIY.org back in about 3 years ago in December of 2014. And we've grown the program from a website to other resources that I'm going to share with you today. We are currently conducting these activities with resources through some grants, one from the Environmental Protection Agency, that's a environmental education program grant to help us build curricula and documentation to support the technology that we'll be sharing with you today, and a grant from William Penn Foundation to help us work with citizen science organizations in the Delaware River watershed and deploy some of these technologies with those groups and help them use the information that can be gathered from them. Before I get into further details, though, I should let you all know that this program is supported by quite a large team, both here at the Stroud Center as well as elsewhere. I'd like to recognize Anthony Oftenkamp at Limnotech and Jeff Horsberg at Utah State, certainly quite involved and helpful in some of the online systems developments that I'll walk you through a little bit later in a few minutes. So what exactly is EnviroDIY in this program? I'd like to put a little bit into context here based on what Stroud Water Research Center does around this program, and start with some water quality monitoring examples, and then talk a little bit about what low cost really means and where cost is at right now before we get into the details. So anybody involved in water quality, water monitoring, has traditionally conducted these sorts of observations in our streams, rivers, lakes, and wetlands. You go to a site, you may just observe what's happening at that site and take some notes down if there's anything to be concerned about, any degradation or obvious signs of pollution. You can make visual observations. You might have an instrument with you to measure some chemical or physical properties of the water body and take a point measurement. Or you might grab a sample of water and bring it back to your lab or send to a lab for some other analyses, nutrients or other pollutants that might be in the water of interest to your program. Perhaps your study sites are co-located with other people's study sites. There's an amazing network nationally that you're probably all familiar with that the USGS operates with stream monitoring stations, gauging stations on our larger streams and rivers throughout the nation. And that's a valuable source of real-time, continuous observation data. If you're rolling up your sleeves and launching a water monitoring program, you may have some resources to deploy some storm sampling or automated sampling devices and collect water samples over, say, every half hour or every hour during a storm. And if you're at that level of water monitoring, perhaps you have data loggers out there already that are sort of autonomous loggers measuring water level, temperature, conductivity of the water, and you deploy those and retrieve them on some timed interval. Of course, all of these things depend on your level of funding and the resources you have to deploy in your monitoring arena. And, speaking of the USGS gauging stations, this is an incredibly valuable resource to have in your watershed. If you're fortunate to have one, there's an amazing amount of information that can be gathered by harvesting these data. And of course, this infrastructure comes at some cost to the USGS and taxpayers. And what this EnviroDIY monitoring program that we've started to get involved with is basically asking the question, can we replicate this sort of sensor station and data access with citizen science programs or in a lower cost arena so we can monitor more streams, smaller streams, or elsewhere in our lakes, wetlands, etc. Similar to the climate monitoring systems that are out there for backyard weather monitoring enthusiasts. So if one is going to start to get into the technology and try and replicate a telemetered data logging station, you would start with the brains or the guts of the sensor station, and that would be a data logger. And if you are thinking about connecting many different types of sensors to that data logger, you may need a relay multiplexer. And then thinking about telemetry, you may be thinking about a radio or a cell module to connect and send those data somewhere to a computer, a server, or the internet. With this sort of approach, typically or traditionally, these devices end up costing in the range of $1,000 to $2,500, depending on the choices you make. And that's really just for the guts of the station. Then you need to consider sensors, a battery or solar panels, waterproofing the system. And so those costs continue to escalate as you move through the construction of your monitoring station. So since about 2010, Shannon Hicks, along with some other folks in our staff, have been working with open source hardware and software to see what we can build in-house and deploy at a much lower cost point. And I'm going to introduce you to this realm of open source hardware software that Brian tried to pronounce, the Arduino family of hardware software in the open source realm, and show you that using this approach, you can probably put together the guts of a data logger telemetry station for somewhere in the neighborhood of $150 to $250. So that's where we're at with meaning low cost on this program. Of course, you still have the costs of buying a sensor or sensors to add to that station, and there are many choices there, just like there are choices in the open source software hardware business to navigate. And we'll go into detail on a couple of these sensors and where you can source these from. That's just a quick picture to show all the different options and choices that can be made for plugging into your device. Now, ultimately, what the Stroud Center has gotten involved with is building some station that looks like this. This is a stream monitoring station that we've deployed throughout the Delaware River watershed with a number of organizations. Maybe several of you on the line or listening have one of these. This is connected to a sensor that is a conductivity, temperature, and depth sensor. It's built by a company called Decagon. They're changing their name at the moment. And a sensor from Campbell Scientific that's a turbidity sensor. And you can see the picture at the right deployed in the stream out behind the Stroud Water Research Center. So this is sort of the end point of what we're doing in this program. So for a station like that, if you source the parts and build this, you can pull this together for somewhere in the neighborhood of $2,000. And really the investment here is in your choice of sensors. The sensors that we've chosen here satisfy our needs for accuracy, precision, and durability. And as you change those parameters, you can reduce costs or increase costs for your sensor station. And then I'd be remiss if not mentioning that if you're telemetering data somewhere, you need to think about the costs of delivering those data through a cell network system to the internet. So there is a monthly charge for the data plan with this particular station. So that's what we mean by lower cost, and that's an example of building an environmental monitoring station to meet water quality monitoring needs. Further definition of what is the EnviroDIY program. We envision this as a place where many different types of people can come together to learn, collaborate, share, and contribute to a knowledge base of how to do all of this and troubleshoot. So how exactly is this EnviroDIY program working? Number one, we have a website. This is EnviroDIY.org. Where one can sign up for a free login and begin to ask questions, share their projects, and get answers to building or working with this open source hardware software environment. Of course, this depends on the open source environment, and much of what we are doing uses the Arduino platform. What is Arduino? It's a hardware software platform. It's also a brand name and a company. However, Arduino compatible devices do not have to be, are not only Arduino brand devices, as you'll see. But there are free downloads for software for the programming environment, and there are stores that sell Arduino hardware technology. There's quite a bit out there about what is Arduino and how does it work. We'll come back to that in a moment. We have a companion website to our EnviroDIY website that holds our code and allows people to access code to program their devices. We use a website called GitHub. This is an open source repository that anybody can set up for their own projects. And we have a URL there that's specific to the EnviroDIY brand where we post our code, but certainly others can share their code or use our code and republish a derivative of our code at this website, github.com. There's a third system that we're working on and building with the help of Utah State University, Jeff Horsberg, and Anthony Oftenkamp at Limnotech, and that is a data submission and visualization system I'll come back to this in a few moments, but this is an endpoint where you can basically tell your device or your monitoring station to send data, and this software system will capture those data and provide some basic visualization tools for you to explore your data. And then the last 2 points of how we're doing this is we're offering workshops and guidance documents to help this do-it-yourself initiative. So a little bit more detail on each of those 7 points. Last month I gave a webinar here that some of you might have seen that introduced you all to wikiwatershed.org. This is a website the Stroud Center maintains where we post tools for watershed activities, watershed monitoring, and modeling. And on this website, we have posted a link to get to our EnviroDIY system. So you scroll down a little bit, and you can enter EnviroDIY by clicking on the visit. Technically, this takes you to a different URL. This is still a Stroud Center hosted initiative, but certainly open to the public to register and share and become involved in this community. When you do, this is a screenshot of the actual website that you would be visiting. You can register on the website, have a login, and you can become a member of various groups and ask questions of the group, share your projects, and share code here as well. So you'll see a number of different groups that may be of interest. There's researchers, Datalogger developers, sensor developers, citizen scientists. I think we have an educators group here as well that's just off the screen that you can join and select to receive weekly emails about any activities or questions that the groups are posing to each other. So a little bit more detail about open source hardware software. As I mentioned, we are working mostly with the Arduino platform. There's the Arduino website where you can access and download more information about the technologies. The hardware comes in many forms. There are off-the-shelf microprocessors or controllers that you can purchase and plug into your computer and program with the Arduino software window, which I'll show you in a moment. The code here is fairly simple to learn. I think with any programming language, there's always challenges for the user to learn that language. But the Arduino platform was developed specifically for the non-technical user. Arduino, the root of the Arduino name actually relates to a cafe in Italy where the founders were having coffee and came up with the idea to build this open source hardware software environment. And one of their motivations was to make technology more accessible for artists and art installations and a very different user group. So you will find the coding a little less challenging than some of the more sophisticated languages out there. These hardware devices can stack, and you can change functionality with different shields or modules. You can add LCD screens or SD cards, GPS chips, or other functionality. With a little skill in programming, then you can make these microcontrollers perform all sorts of functions, not necessarily just for environmental monitoring. These could be to water a plant or open a garage door or other tasks in the Internet of Things world. So about 5 years ago, 6 years ago, Shannon Hicks, our electrical engineer on staff here, started working with the Arduino devices to solve our monitoring needs and worked through the different products that are available and eventually realized that we had many more functions that we were desiring out of this microcontroller than the products on the market currently had available on a single board. So Shannon designed her own circuitry board, and we have fabricated this and produced a number of these for our own use, and now make these available to the public for purchase. This is called the Stroud EnviroDIY Mayfly Datalogger that you can see on the far right of the screen here, the green board at the right. And of course that board has gone through a number of changes over the last 4 years, and we're currently on version 5. The layout is stable. There are subtle changes to the functionality here. And I'll just quickly show you this screen that compares the features of the Mayfly logger with the Arduino Uno, which is one of the more basic Arduino boards, to give an idea of the memory and the functions and features available on the Mayfly logger board. I'm not going to go through all of these functions and features. That would be the subject of a little bit longer workshop that we offer. But suffice it to say that this board has quite a bit of functionality and flexibility for building environmental monitoring sensor stations. We've even posted a getting started tutorial on the EnviroDIY website for working with this particular microprocessor that's Arduino compatible. And we've also provided some links here to show you how to get to the software environment for programming these boards. When you visit this page, you can click on software, and there's some basic instructions for configuring the software to work with the Mayfly logger. But you'll be directed to arduino.cc to download this desktop software. When you go there, here's the Arduino website you're directed to, and under software you'll see a couple choices. We usually recommend people download the Arduino IDE and install that on their machine. And there are a few other steps to configure that piece of software so that it can communicate with the Mayfly logger, and those steps are outlined on the website here at EnviroDIY. So once you install that and open that window, you'll see a programming environment where one can build the Arduino code to tell your microprocessor what functions you'd like it to do. These codes are referred to as sketches. So if you're new to the Arduino world and you start searching for different programs to tell your data logger what to do, you'll probably be using the terminology sketches rather than code. There are sketches that are posted out there for free download and reuse, and you can search the internet with different key terms depending on what you're looking for. Of course, we've included the sketches for the Mayfly logger either on our website, on the website at EnviroDIY.org, or on that GitHub repository. And basically, you can find somebody else's code, copy that code onto your clipboard, and paste it into this programming window, and make some minor changes to the code if you like, and then upload the code to your microprocessor to tell the microprocessor what you would like it to do. So here's our code repository on GitHub, where you can find our sketches or others derivatives for working with this particular data logger, the Mayfly data logger. If you're completely new to the Arduino world, this has been around for a while, and there are a lot of resources out there, lots of books for different skill levels, entry level to more technical level programming explanations, and learn the hardware kind of tutorials. So, once you have progressed to that point and you're building a sensor station and thinking about coding it, you're thinking about where do my data go, you might data log to a card, an SD card, and download that on your own computer. But we think the real value here is having online, real-time telemetry from these stations. So there are a couple options of where do you send your data. You can build your own website. There are plenty of folks, particularly at universities, engineering departments, where students are building their own data submission and visualization websites. Shannon has built a website here to host our projects using a free web service called dreamhoster.com, where we can send our data and have real-time access to the time series from any of those sensors. Of course, the devil's in the details here as far as coding and web services that you may or may not be situated to do yourself. So with that in mind, we've been working with folks at Utah State to develop a web system, software system, where you can register your device and have that connection happen. The website we've developed is data.envirodiy.org, and here you can register and then request a site and define your monitoring site, the location of the monitoring site, and the types of sensors that you are deploying, and eventually have the code or the URL token to copy from this website, put onto your hardware device through the Arduino software programming process that then instructs the Datalogger where to send these data to this system for data visualization. There are summary graphs here that show the last 72 hours of data, but there's also access to a time series analyst that will allow you to interrogate the entire period of record for your time series data and or download these data for you to manage and archive yourself. If the group has more questions about the technical details behind that, I would refer you to Dr. Horsberg at Utah State. Recently presented this architecture poster at the American Geophysical Union annual conference. So this slide is not intended for you to read, just to be aware that we can provide you a little bit more information about how that system works if you're interested. So the last two pieces of the puzzle here are the workshops that the Stroud Water Research Center has been offering, and that potentially other entities that are sort of the train-the-trainer model may eventually offer a workshop similar to this. But the workshops that we've developed range anywhere from 4 hours to 3 days, depending on the needs and the arrangements that we make with the host entity for these workshops. But our full 2-day, 2.5-day workshop covers all of these components. We introduce attendees to the hardware, to the software. We actually have folks plug the devices into the computer, open up the programming window, and get comfortable with reviewing somebody else's code, not necessarily programming themselves. Building the monitoring station, how do we take this technology and put it in a waterproof box, and how do we, once deployed, think about whether there's risk of vandals or animals or storms that might destroy our hardware out in the field. We talk a little bit about quality assurance, quality control for maintaining high quality data coming from these stations and the maintenance that's required, as well as introduce attendees to the details of the data capture, data visualization, data management interpretation analysis. So that's a lot to cover in 2 days, and I think that helps people, though, scratch the surface and get comfortable with the program moving forward. A few photos from some of our workshops where we've done this, and we're getting good feedback from attendees to continue to refine our materials and our workshop process or organizations. Attendees plug these devices into the computer, even connect some educational sensors to the device, and look at data collected by the device in real time on their laptops. The Stroud Center has a traveling classroom of laptops that we can bring with us, as well as some of the equipment, the hardware, to share with the groups that we offer workshops for. We take attendees through the building process, showing them a couple strategies for building waterproof cases, and ultimately we end up with our end product here, this conductivity, temperature, depth, turbidity station, and we take the group out and we deploy these depending on the venue where our workshop is in a water body, and talk about strategies for deployment, challenges. Of course, we go over in detail many of the options for different types of sensors that one can begin to control with the Arduino technologies. Some of these are easier to program than others. Some of them are cheaper than others. And your choice of sensors is typically driven by those points I made earlier, the desire for certain accuracy, precision, and durability of the sensors. These are almost all commercially available bare wire sensors. So these are not necessarily fabricated by the Stroud Water Research Center or any attendee at any of these workshops. You'll see some perhaps common, well-known brand names here that are making these bare wire sensors that can plug into various data loggers. We also go over some different examples or different options for the telemetry side. Of course, the ability to telemeter via a cell network is always dependent on where you're going to deploy your sensor station and what the cell signals might be out in the wild of wherever you are thinking of putting your monitoring station. So that's the program in a nutshell. There are a few pictures here I have to share with you to show you some installations that the Stroud Water Research Center has been involved with. This one's right out the back door of the Stroud Center, connected to a conductivity, temperature, depth, turbidity station, along with a light sensor there. Right at the top of the pole, there's a black sensor that's a light sensor. Here's a station nearby the Stroud Center during a flood in White Clay Creek. Here is one of our stations deployed adjacent a farm field, where we have a study looking at how water and material move off of a farm field during storms. Another installation where we have constructed the sensor station to connect to soil moisture probes that are in a soil pit to help us understand soil, the physical processes of water moving through soils. We've had a couple opportunities to be in the not marine but estuarine environment, where there are other challenges of dealing with semi-salty conditions. Certainly from a materials standpoint, your choices of stainless steel versus other equipment are really important there if you're working in estuarine environments. And then there are other sorts of critters that float by the sensor station here. You can see the jellyfish on the right next to the sensors that are on a sandwich cutting board or a meat cutting board, But here there are three sensors, the CTD, an optical dissolved oxygen, and a turbidity sensor mounted on that board. So you can see that there are many different ways to customize the open source hardware, software systems to meet different monitoring needs. There's a collection of other sensors here that I haven't talked about too much. The bottom panel, second from the left, is a tipping bucket rain gauge. The top middle picture is an ultrasonic sensor measuring distance to the water rather than a pressure transducer. So there are many different choices. Depending on your sensor, you get certain types of data back. Here are some examples of conductivity, temperature, depth, and turbidity sensors that we've deployed. The top panel has a time period of about a week in August on the x-axis, depth on the left y-axis, which is the blue line, and conductivity on the right y-axis, which is the red line. And you can see the dynamics that happen when it rains. Depth goes up with the blue line going up around August 12th, and conductivity of the water being diluted because rainwater has very low salt content washing into the creek. And then the rebound after the rain with the stream level dropping and conductivity moving back up towards that groundwater conductivity signal about 300 microsiemens. Bottom panel is a little bit shorter time window, focusing in on a storm event where blue is depth and green is turbidity. And you can see that during this storm, turbidity rises along with the storm. Another data example showing the influence most likely of road salt on conductivity. This is apropos for this time of year, going into winter. We see this pattern happening quite regularly in our sensor stations out there. Again, red line is conductivity, blue line is water depth. And when it rains or we get a sort of slushy snowmelt event, here we have the stream going up and the stream depth going up in blue. And here we have conductivity rise during that runoff event, most likely because of the significant amount of road salt washing into the creek. So this gives you a little bit of an idea of what some of these sensors measure and some of the interpretive value. Here's another fairly complicated example, but from a little bit different perspective. The top two panels are from an April time period, 3 days in April. And I have a sensor station located in the meadow in yellow, and green is in the forest. And the left panel shows the light climate. This is the photosynthetically active radiation from one of the sensors. And on the right panel shows water temperature. So we see the April time period where the meadow and the forest are close to each other with light climate and temperature, but in July the light climate and temperature differ dramatically from these two sections, primarily due to the leaf out period and the shading that forest provides in our stream ecosystems. So third example of the type of data. All right, I'm getting close to time expiring here, and I'll try to wrap up with just a couple more slides. You can see why we're doing this. We feel that there's this need for continuous real-time monitoring. The rationale here is going to be really diverse. It's going to depend on your interests, your motivations for doing the monitoring. The technology is becoming a little more simplified. There's certainly more sharing of information in the open source world to help troubleshoot or learn how to do it yourself. There is a need for greater data transparency, a need for lower cost solutions. Even the solutions I'm showing you here aren't quite what we would all want to define as low cost, but the costs are moving in the right direction. So what is this thing again? Come back to it. Hopefully you'll see it's whatever creativity you have. It's whatever you want it to be. We have examples of how we use it. We're looking for creativity. We're looking for people to share their solutions or their work on the EnviroDIY.org website. So hopefully motivated or stimulated some of you to participate, or share with your other techie colleagues to participate, and consider doing some of this yourself and adding to the crowdsourced development of this program, because we think that this will result in lower costs in the future, more data, more easy to learn, and of course all of this is leading, we hope, to more environmental information, monitoring information, spatially, temporally, as well as paying attention to the quality of data. So please contribute. I'm going to anticipate one set of questions here, and that is, where do I buy the hardware? I'm not here to advocate for one product over the other, but there are many vendors, and you can use search terms to find Arduino hardware or open source hardware electronics. You'll come across a lot of different options. I've provided some links up in the corner of some stores. Arduino has a store, Public Lab, SparkFund. I know Shannon can share with you many different places where these products can be purchased. And we've made the Mayfly Datalogger boards available via Amazon if there's interest there. These are sort of extra stock that we have from our own projects that we put there for anyone else if they're interested. So with that, hopefully the volume and the slides all worked and you have some questions. Open it up for questions.
Yep, thanks, Dave. There are a few questions, and if folks have additional questions, we do have a few minutes here if you want to go ahead and type those in. There were several questions in here about the workshops and the cost for the workshops and any kind of rough schedule where they can find the workshops. Can you give more details on those?
That's a great point, and that's an oversight on my part. I should have put a slide together for that. So if these are workshops within the state of Pennsylvania and the organization requesting the workshop is able to apply to DEP's Growing Greener program, then we are part of a consortium for scientific assistance to watersheds that receives DEP funding, where we can pay our costs for having a workshop for attendees. But what we can't do is give away or pay for any free hardware. We can bring our hardware and our laptops for the workshop, and we hope that it leads to eventual deployment of the monitoring technologies. But certainly this is a way that we can cover costs within the state of Pennsylvania. If you're outside the state of Pennsylvania and you'd really like to think about a workshop with us, you can contact me. We'll have to find a way to fund our costs for doing such a workshop.
Okay, and as I bring up the next question, I'm going to pull up our first poll question, which is the standard questions we always ask at these webinars about how much you learned today. And the next question on here, I think you might have already answered. It was related to combining with meteorology rain gauges. You did show one example of that. They give the example of weather underground, but it looked like you do have that capability. Did you want to add anything to that?
We certainly can add tipping bucket rain gauges and other sensors that are meteorologically oriented. The data.envirodiy.org data hosting page is not yet set up to host data from those sensors, but a request can be made through the website to add that particular sensor's data stream to the list of options.
Okay, and I'm going to pull up our second and last poll question here, which is just about any actions you might take as a result of watching the webinar. And the next question on here is about, are there any examples of data collection at the same location with both a Mayfly data logger station and one of the expensive systems that a government entity might use? And basically asking about comparison of accuracy.
Yeah, this is Shannon here. I'll answer that one. We have been we've been doing that on our own at our own sites here at the Stroud Center. We've got several of the commercial data loggers and data systems and sensors and like complete package systems that we've deployed here over the last 6 or 7 years as we were testing all of this technology. So that gave us a really good test bed here in our backyard where we could verify that our homemade stations were working just as good as something else. And in the past couple of years now, we've been co-locating or installing sensors at a variety of locations away from the Stroud Center, including some where one of them there's a sensor probably just 10 feet or so from a USGS gauging station. So we can go online and see our live data from our Mayfly station right along with the USGS gauging site, and we see that we're getting exactly the same results on the two stations. So that's just another proof that the validating the results we're getting. But because we're using commercially available calibrated high quality research grade sensors, we should not expect to see any sort of difference between them because we're using the same sort of sensors USGS is. It's just that the data recording device and the telemetry system we use is much lower cost. So the thing that's actually in the water doing the measuring is still the same level of accuracy. It's just that we save money on the rest of the hardware out of everything. So by co-locating them in those locations where we're able to do that, it's been really helpful to show that validation. And we've had that going for a number of months and a couple of years in some cases.
And I would just add that if you're thinking about doing this, the commitment to maintaining your sensor station is not something you should just brush aside. You should think very carefully because really getting good data out of these stations requires maintenance visits, cleanings, and checking on them on a regular basis. And there's protocols out there that the state has for continuous in-stream monitoring and how to care for your sensor stations and how to treat your data once you have them as well and manage them.
Okay, we have a few minutes left. A couple quick questions. I'll ask these together. One is how simple is sensor calibration using the Mayfly? Are calibration sketches available in the repository? And then the person asking about grant assistance availability.
I'll talk about the calibration side of things. A lot of the sensors we use come already calibrated from the factory, so they will have like a digital output on the sensor. So when you plug it in and power it up, it sends out a serial stream with just an ASCII number in it. So there's really nothing you can do to calibrate that because that's just the way the sensor works. There are other sensors that we have, like the turbidity, that is an analog sensor. So we're measuring an analog voltage, and then they give you, each specific sensor has a serial number, and I have a sheet of 150 or a stack of 150 sheets of calibration curves for each specific probe. And if we move one probe from one Mayfly to another, we have to put that calibration information into the sketch. So there is a line or two in the Arduino sketch that gets written to the board that says we are using serial number 9972, and here's the calibration curve information for that. And so we do have to make sure that we track that, just like you would with any other data logger. But then we also do just the usual checks and standards that you would with any instrument, where we use calibration standards in the lab to ensure that the sensors are working properly from the factory, and then we do field calibrations and checks when we're out in the field, either with the instrument itself, or we bring a handheld meter and take spot measurements at the locations on a regular basis to double check that the readings in the field are accurate. So we're doing the same sort of legwork we would with any other system. And as Dave said, the cleaning and maintenance at the station is really important, because if it gets neglected over the course of even just a few weeks at certain times of year, some of these sensors will be reading some invalid numbers. So keeping accurate records on those maintenance schedules, and cleaning visits is also important for our data QA/QC. So that's one of the things that we have with that whole data.envirodiy.org site, is a way to help keep track of not just your installations of the site, but your maintenance visits and cleaning, calibration checks, and all that, so that you do have a full data record, not only of just the readings of the sensors, but all the calibration work that's gone into to proving the validation of the measurements. And I think I'll let Dave answer the funding question there.
Yeah, so grants, I mentioned our ability to cover workshop costs with Seesaw. The work that we're currently doing, funded by the William Penn Foundation, is grant-funded work where, you know, we wrote a grant to establish this program and work with organizations in the Delaware, and that grant is paying for the hardware software costs of deployment that we're working with each of these organizations throughout the Delaware with. So there are about 60 stations that are going out. We are nearing the end of that grant, and I have most of the 60 stations already accounted for in the Delaware. So the way that we work is we're happy to pursue grant funding with partnering organizations to pay for the cost of the hardware. If you'd like to contact me, I'm happy to entertain working with you all in that capacity, or giving you some advice on how to formulate a proposal, what the cost might be for starting to work with this technology.
Okay, we have just a couple more minutes and just a couple more questions here. One is specifically about that USGS station next to your station. Is that data available to the public? I guess I would assume it is, because their data generally is, but is there anything specific about that station?
I know for sure that those data are real-time available to the public on the USGS, what is the stream, real-time stream monitoring USGS. Just search that on the whatever search engine you have, and that particular station was White Clay Creek at Strickersville. But there's
Brandywine,
yeah,
Brandywine Creek.
We're fortunate in the Christina River Basin to have a very strong network of USGS hydrologic monitoring stations.
Okay, so Kim just clarified and said she meant your data as well. Is that data publicly available?
They are. Most of our stations are on the web. I'm not so clear on how well the search engines find them, but if you're interested, shoot myself an email or Shannon, and we can share with you where those data are.
And then maybe just to wrap up, a couple of technical questions here. Is there updated info on cellular telemetry? The modems they see in the forum seem out of production, and is there a way to support 12-volt sensors?
What was the last part? Global what?
12-volt sensors.
12-volt sensors.
Actually, the dissolved oxygen sensors that Dave mentioned earlier are powered by 12 volts. The Mayfly itself can handle anything from a 3.7 volt lithium battery up to a 16 volt car battery, or if you have a regular 12 volt battery and you got solar panels, it goes up to almost 16. So the Mayfly has a wide input range for powering it, and then sensor wise, you might have to build some adapters. We do have some. I custom make them all for myself. We don't have them currently available, but if somebody needs one, we can share our plans for how to do that, and that may be something we offer later. But yeah, you can power a wide range of sensor options and sensor power options. So that's not. What was the other question?
The cellular communications.
In cellular, there are there's 2G, 3G, and 4G options. In the U.S., 2G is used to be fairly cheap and pretty easy to find, but it's been being shut down, and as they are opening up new equipment for other versions, and so we're working on coming up with other hardware options. Once we find, we do have 3G and 4G hardware options for the Mayfly, but we're just working on finalizing the software that the Mayfly talks to those modules with. So Currently, the cheapest, easiest thing to do if you have 2G coverage in an area is just to use it's a $30 module, and it uses an $8 a month cell plan. Modules for 3 and 4G cost 2 to 3 times more for the hardware, and the data plan costs almost $15 a month. So it's cheaper if you can use 2G, and 2G should get us until about 2020 when that's retired, and there'll be probably all new hardware by then anyway. So for the next several years, we should be good with 2G. And anywhere outside the U.S., 2G is still the preferred methods, and so the little 2G modules we use can be found anywhere, and can be used anywhere outside the U.S. More easily than they can inside the U.S. The one issue is there's only one manufacturer of those little modules right now, and he's out of stock, but he should be having more soon. So we occasionally have questions on the forum about people looking for those. So the hardware is a little hard to track down sometimes because it is so popular. There's just not that many sources for it. And currently the Mayfly is actually out of stock. The starter kit, if you happen to look for it on Amazon, it's out of stock right now, but we will be getting it back in right after the holidays. So, and we'll be replenishing our supply of the regular Mayflies also.
Okay, well that takes us to the end of our hour, so I want to thank Dave and Shannon for a great webinar. I appreciate them taking the time to go over this with us today, and appreciate everybody attending today as well. If you are somebody that's watching a recorded version of this webinar, if you will click on the link on the screen, it will take you to a very short survey about what you thought of the webinar. So that's just for folks that watched the recording. And then finally, just holiday wishes from the Penn State Water Resources Extension team. We thank you all for attending all of our webinars over the last year, and we look forward to presenting some more webinars in 2018, albeit on a little different schedule, but we will still have some webinars next year on various water topics. So thanks again, Dave and Shannon. Thanks everybody for attending, and we'll see you in 2018.
Thank you all. Happy New Year.